This first sequence of videos is going to focus on some of the ideas necessary for collisions. Note that in physics, we define many types of interactions as collisions pretty much any time that you have two objects that are coming into contact for a short period of time or coming into contact and then staying together. So one example would be two billiard balls hitting each other where one comes in, hits the other, and then they both move off. So in this case, these are free objects that you don't necessarily think of any forces interacting on them other than the interaction force when they collide. A second example is a racket hitting a tennis ball. Now you don't see the rest of the racket, but you can imagine that a person is holding it. And in this case, the racket is having a force exerted on it by the person, but then it comes into collision with the ball, and then the ball has forces exerted on it by the racket. The ball also exerts forces on the racket. So there could be situations of blobs of clay hitting one another, carts coming into contact. There's going to be many different things. So think about collisions in a very general sense here, not only in billiard ball sorts of situations and not only sports analogies. So we need to introduce some new ideas to deal with these. And so we're going to go a little bit backwards in a way, but we're going to start by thinking about a ball colliding with a wall. We're going to think about the forces involved when the ball is in contact with the wall. And this is now a different sort of situation than we've had before because we now have non-constant forces. We know the ball comes into contact with the wall exerts a force on the ball because the ball's velocity is changing, and we don't really know anything about this force. We can sketch it out this way, assuming that the force increases and then decreases as the ball collides and kind of collapses a little bit. You can imagine it getting a little squished and then it expanding out. But of course, this is just a sketch. This would be really complicated to calculate. So this is important to recognize is the reason we're introducing these new ideas is that it's very hard to actually deal with these forces in an exact way. The models we've used before, using Newton's second, third, first laws, those all assumed in general for our work constant forces. So we now have non-constant forces. They're not constant in time. Note that this is a plot with respect to time. We see it changing. And we're going to call these impulsive forces. They only exist for a short period of time while these two things are in contact, but they maybe have a complicated shape and only a short period of time. Okay, so that's kind of where this is coming from, that we need a new idea in order to deal with that. And one of the ideas is going to be impulse. The impulse is going to be a way of describing this force, and spoilers, it's going to be the integral of the force over this short period of time. So impulse is the idea that we've changed something about the ball due to this force acting over a certain amount of time, but we're going to work with it in a way called impulse because it's difficult to work with the force in an exact way. And the thing that's kind of the big idea here is momentum. The impulse is going to be related directly to momentum. We see that a property of this ball is changing, and you might see that it's really the velocity. Initially, the velocity is going to the left, and afterwards, the velocity is going to the right. Since velocity does change, if you've changed the direction, we see that velocity is changing, and that's going to relate to momentum. So the reason that we're introducing momentum and impulse is to deal with these non-constant forces. So what is momentum? Momentum is a quantity that depends on mass of the object and the velocity. So in general, it's just going to be mass times velocity, and note that we're defining this for one object. So if I wanted to be careful with my notation, I might say that this is momentum 1 equals mass 1 times velocity 1. Note also that we're using lowercase p here, and this is for one object, so you're going to use subscripts along the way. Later we're going to use capital P for something else, so do be careful with that. This is a vector, right? We're not saying that it's mass times speed, we're saying mass times velocity, and velocity is a vector. So this is important because it means that when we deal with momentum, it's going to point in the same direction as velocity, and we can then break it into x and y components. It's also important that you use signs. In many situations, we're going to be dealing with this in one dimension, but keep in mind that if I have my positive x hat direction and my momentum is pointing that way, we would say that this is negative p, right? So this is a negative px component. So please be careful with your signs. So the last thing to recognize is that you can have two objects with the same momentum that actually have very different masses or very different velocities. Because it's mass times velocity, you can have a slowly moving large object or a quickly moving small object in terms of its masses that really have the same momentum. So keep in mind that it depends on both of those things. Lastly, we can relate momentum to forces, and what we have to do is work through a little bit of calculus here, and the book goes through some additional derivation of how to get impulse and how we relate change in momentum to forces, but I'm just going to start with a little bit of it since we can probably think through this fairly quickly. We can take the time derivative of momentum, and before we do that, we would want to expand it as mass times velocity, and we want to keep that vector part here. Now, if mass is constant, then we can just distribute the time derivative and say that the mass is a constant up front, and we're left with the derivative of velocity with respect to time. Note that there are situations where the mass is going to be changing in time, but let's just start with this simple case. So then, we remember that the time derivative of velocity is just the definition of acceleration. And so we see then that the time derivative of momentum, just written in slightly different ways here, is equal to mass times acceleration, which was the definition of force. So we can actually define a force to be the time derivative of momentum. And the reason that matters is we can then think about this in terms of an integral. So if we just integrate force over time, we then would see that we're actually just integrating our time derivative of momentum, and so we're left with a change in momentum. So that's how we're actually going to relate this to impulse, which we'll do next.